do need to do that for you. All right, so I'm going to go ahead and scroll. All of this is in the book, though. When you see something like arcsine, it's not necessarily written the way that you're used to it. The way that you're probably used to it would be an inverse sine. They are the same thing. And remember, an inverse sine is if, say, y equals the sine of x. Actually, let's not use x. Let's use thetas. Then, by definition, the inverse sine is what you get when you plug the ratio in and you get out the angle. And realistically, it just depends on which textbook you're using as to which one they use. And in fact, I've seen some textbooks where they just jump back and forth between the two. For whatever reason, your textbook uses arcsine on all of the problems I was looking at last night. Whereas your old textbooks probably use the inverse sine, but they mean the exact same thing. It's just another way to write it. And as you go off to college, just expect that you could see either one. Again, I'm not positive why we have two different versions of the same thing. It might be that some people got confused by this notation, because remember, this does not mean 1 over sine. But typically when we see that -1, that's what it means. Like if we see it as an exponent, that's what it typically means. All right. So, couple things that we need to remind ourselves of when we're talking about the properties of these inverses. The first thing that we need to talk about is domain and range. So, we'll pause for a moment while you finish copying what's on the screen. This is why I appreciate cameras, because I can tell. Without cameras, I'd just go for it. All right, thank you, Claire. That helps. Okay. Go ahead and get this ready, but realistically what I need is over here. Now, you may remember that y equals the sine of x gives us this wave line. And if we were to take the complete inverse, then let's see. This has a height of 1, so we would never pass 1 here, and it's got the lowest point is -1, so we would never pass this here, because remember, you switch your x's and your y's. Let's see. Be about here, it looks like, that we'd hit that point. I'm just trying to eyeball this. Be about here. We would end up with something. This definitely will not be exact. Okay, but if you have graphed the inverse, you know that this is not the graph that we get. So, if we graphed the entire inverse, it would look like this. But the inverse functions are ones that we cut, Because when I talk about, and there's a very important, where do I say this? Inverse functions, what is the problem with what I just drew on the screen?
It's not a function.
Why? How can you tell?
Well, I mean, if you do the vertical line test, it overlaps like every time it goes back on itself.
If we do the vertical line test on our situation, we're going to cross our function an infinite number of times, and by definition, it cannot be a function if we're crossing it more than once. Which is why, if I were to graph this, and maybe you did this... Oh, go ahead, Cormac.
I was about to draw it out just based on what I remember. Isn't it like... This is going to be a very rough drawing, but... Isn't it more like that? I don't know if you can see that.
I'm kind of blinded by the paper. It's not showing through very well. But I am about to show you, so... Actually, let's go ahead and write it in the arc. Just show you that one. Arcsine of x. And let's go ahead and take away everything that I drew. It just gives me that piece. Is that what you had? Yeah, so we just have this little piece. And the reason that we do this is for the arcsine, the range must be limited in order to have a function. And so if I think about y equals sine of x and look at its domain and range, I can see the domain goes on forever. Are you familiar with this symbol? I'm not sure if I've used it this year or not. This funny looking R. JC says yes.
Isn't that all real numbers?
That means all real numbers. And remember, my range of the original function, it only goes between -1 and 1. And again, this is the original function. With my inverse, things swap, but not perfectly like we're used to. So my domain does swap perfectly with my range of the original. I am going from -1 to +1 on my x-axis. But my range is the thing that works differently. If I were to swap exactly, I'd get all real numbers, but then I don't have a function. So the way that it's cut is it's going from this highest point on the sine to this lowest point on the sine. Or I should say from low to high, realistically. So, erase that for a moment. Do you remember what angle gives us this lowest point right here? And keep in mind, because it's on this side, it is a negative angle. And also keep in mind, it's going to use pi. All right, you have your unit circle handy? If you have your book, you have your unit circle handy, because you just have to flip the page of that first flap, and it's got a unit circle right there for you. So remember, on the unit circle, your sine of x corresponds to the y values. So look for the smallest y value and tell me what angle gives you that y value. And the angle is written in blue on my flap. So I expect it is on yours as well. Now granted, it's not going to be a negative angle on the unit circle, but we can convert that easy enough. Look for the smallest y value, the lowest y value, and tell me the angle that corresponds.
You said pi?
It's not pi, but that is a very good guess. That would give me 0 as a y value, and I do have some negative y values, which would be smaller than 0.
Would it be 3 pi over 2?
So that 3 pi over 2 gives me a y value of -1, which is the smallest y value that exists there. All of the other y values have those square roots in them, so they're not necessarily numbers we know off the bat, but we can see that we go lower and lower and lower, and that's the lowest point on the unit circle. Now, this point right here would be 3 pi over 2, because I mean that's a positive number, and this is the positive direction, this is the negative direction. So we need to find the angle that corresponds but's in the negative. And the easiest way to do that is, this is one complete cycle. Let me change my color again so I'm not overwhelming you. This is one complete cycle right here. And it takes 2 pi to go a complete cycle. So to find this point right here, all I have to do is I have to take the point on the unit circle and subtract 2 pi. So our range here is going to go from the negative pi over 2 to the positive pi over 2. It's one of the few times where you're going to see your inverse not behave the way we're used to inverses. You're not going to see your x and y properties exactly flip. And it's because mathematicians made the conscious decision to cut the inverse function so it could be a function. Because without it, they get an infinite number of answers, and they don't want that. Now, one of the things about this that you are going to have to recognize is sometimes the inverse function doesn't give you the answer you want or need, and sometimes you have to do a trick like we did up here, where you're going to have to add or subtract 2 pi to get the one that they're looking for, the specific angle that the problem is looking for. It's something you have to deal with inverse when you do inverse trig functions that you don't have to deal with in other places. Okay, and I'm just pausing until everybody's finished writing, so I'm not going to go through all of the trig functions, but I am going to show you the cosine and show you how that one has a different range than the sine, and explain that to you. And then we'll just give you the rest of them. All right. Give me a thumbs up if I can go ahead and take this off the screen. Jared and Cormac, what do you say? Can I take it off the screen? Okay. Jared, can you hear me very well today? Maybe, maybe not. Okay. So let's show you for the cosine. We see a very, very similar situation here. If you were to draw in our situation, and what I'm going to do is I'm seeing I have, say, the point right here is 0, 1. It takes one complete cycle. This would be 2 pi comma 1. This point is going to be pi comma negative 1. And then this would be pi over 2 comma 0. And 3 pi over 2 comma 0. So I'm going to need to take those points and switch the x's and the y's to get what I'm looking for. So I'm going to have the point 1 comma 0. I'm going to have the point 0 comma pi over 2. Let's see. For myself, I'm going to step this in terms of pi divided by 4 on the y's so I can see these points better. Didn't know you could do that, did you? Alright, so 0 pi over 2 would be right here. Negative 1 comma pi right there. 0, 3 pi over 2. 2 pi 1. And I get out something that looks like this, and then will repeat itself. Now this function has to be cut as well, but we have an issue if we try to cut it the same way we cut the last function. The last function, your arcsine, had a range, and you don't have to write this down again because you had it on your paper right in front of you, but its range went, let's see, I've already confused myself for a second. It went from negative pi over 2 to pi over 2, right? If I try to do that here, that means I'm going to go from this height to this height. And what's the problem if I try to cut the function there? What's the problem if I get rid of all of this and I get rid of all this? That pink part that's left in the middle. Nalina.
It's not a function.
It's not a function. It won't pass the vertical line test. So I can't cut it the same way. So I have to look for a place which will allow me to have a function, and we just look for the easiest place, the place that still is right around your origin. And so the way that we cut it here is if we cut it here to here. It passes the vertical line test everywhere in between those lines. And so if I were to graph the inverse cosine, and get rid of everything on my screen, I see I only get that point where it's above the x-axis. So on this one, where my cosine of x has a domain of all real numbers and a range that went from -1 to 1, when I look at my inverse cosine, my domain does translate over. I do still go from -1 to 1, but of course, since it's a domain now, it's my x's. My x and my y properties switch. But on this one, the y values only go from 0 to pi, not from -2 pi to or sorry, negative pi over 2 to pi over 2. So if you can't remember personally what the domain and range of that function are that you're working with, just graph them. Just graph them and look and see what you've got. I will admit that on part of the AP test, you won't be able to do that because you won't be able to use a graphing calculator for parts of the AP test. But realistically, that's not going to be many questions you're going to have to deal with. Like, it might be one question on the AP test where you'd really have to remember those facts, where they might be trying to trick you. Now, for these other ones, I'm not going to prove them to you. I'm just going to give them to you. If I can move stuff on my desk without knocking anything over. Actually, let's just go ahead. Sorry if you've already written this down. I'm going to put the two that are similar to each other next to each other. Okay, does anybody still need what's on the screen? Nalina, that was fast enough. I couldn't tell if you were waving at me or if you had a thumbs up. Okay. Nalina, are you still copying down? I can't tell.
Yeah, I'm good now.
Okay. Okay. Try to tell the body language from the forehead. Doesn't always get across. Okay, so let's do, and I'm only going to do a couple of these, solving equations with inverse trig functions. And then we're going to get ourselves into the calculus of it all. So ultimately, you have two ways you can think about this sort of problem, and it doesn't always matter which way you pick. So we could solve this problem by saying, this is going to give us some ratio. I know that if I take the sign of that question mark, I get out the ratio -1/2. And then we can think about, okay, here's how I rationalize my way through, by the way. Just because I don't always have a unit circle on me, I think about a regular triangle. And I know my opposite side is going to be 1. Of course, granted, -1 here, but I can think of it as the 1. And my hypotenuse is 2 because this is opposite over hypotenuse. And then I think through which special triangle had the ratio where one side was 1 and the other side was 2. It is a special triangle. They're going to give you ones on purpose almost always that are going to be special triangles. I know because of my rules of Pythagorean theorem, and this is a special triangle I memorized, that this side would be a square root of 3. And the triangle that gives me this is the one that is the 30-degree triangle. I recognize you might not have those triangles memorized at this point, but somehow having the unit circle memorized is going to be helpful to you. And for me, using those special triangles is how I rationalize my way through. Now, I do have a y value here of -1, so realistically this is going to have to be a -30. And because we're in calculus and we're not using degrees, I'm going to get out that the arc sine of -1/2 will be a -π/6. And here it probably would have been more appropriate for me to have drawn my triangle down here to show that that is a negative. The other way you can handle this is, it is true because they're inverses, you can take the sine of the arc sine and because they are inverses, these cancel out. Actually, no, with this problem I wouldn't do it that way. We will get to problems that use this, but I wouldn't use that method here. So ignore that. Let's do that on one of the later problems. That's more helpful when x is inside the function. If you're trying to find the arc cosine of 0, you have to think about how this means that the cosine of your angle is equal to 0. And think about the unit circle and where does that equal 0. And there are, of course, 2 locations, but because we're looking at the limited range here, your cosine, well, let's write it this way. On the unit circle, your cosine corresponds to the x values, and your x values equal 0 right here and right here. So that was at pi over 2. And the way we're thinking about this right now, this is going to be a negative pi over 2, even though we're more used to seeing that as 3 pi over 2. They're coterminal angles. And based on what we wrote earlier, which one of those falls into the range of our arc cosine? We wrote it at the range of our arc cosine earlier.
Pi over 2.
Your pi over 2, because your range of your arc cosine goes from 0 to pi. Negative pi over 2 is not inside of that. And I do see on your faces kind of some looks of this probably feels more new to you. Which, remember, I mean, honestly, we've brought it up almost every class. The situation with math was different last year. This is probably one of the things that got glossed over if this feels new to you. And that's understandable. I'm not going to spend the lesson necessarily focusing in on this, but you can send me a request to do a video just on this stuff, and I'd be happy to do that for you. Okay, now this is where my other method's going to come into play, because we have x on the inside. Our unknown is on the inside. So you do have 2 options here, and this is going to be where it's just going to be up to personal preference. You can either do some rearranging and say that, well, I know that this means that the tangent of my angle is equal to what's on the inside. Or you can use the idea that, and ultimately they mean the same thing here, that if you take the tangent of an arctangent, so in other words, if you do something on one side, you do it on the other. Inverses cancel. And we'd get the exact same thing. Either way we look at it, whether we just treat it like I'm just going to rearrange the problem, or if we treat it more like an algebraic process of you do something on one side, you do it on the other, you take an inverse. They both will mean the same thing. And then after you've done this step, it all turns into a basic algebra problem. I'm going to use the one on the left to finish it off. And you do want to simplify the tangent of pi over 4 or whatever your trig function is. And so I threw the special triangle that relates to pi over 4. And remember, pi over 4 is the same thing as a 45-degree angle. And I'm going to take the tangent of that triangle. So the tangent is the opposite over the adjacent, which is very convenient because it's just 1 over 1. Gabe, you writing this down? Okay, and be honest with me for just a second. After we just flew through all of that review of inverse trig functions, how comfortable do you feel with these inverse trig functions? 1 low, 5 high. Show me with your fingers, or tell me in the chat. Okay, yeah, that's kind of what I'm expecting just based on how much time I think we spent with them last year. Even for those of you that had me last year, we did use them. Okay, good, Cormac. Yeah, we did use them, but we didn't necessarily use them a lot. Yeah, I'll think about doing a video for you. I know my schedule's a little bit tight today, or it might end up being, but I'll see what I can do. Okay, but I am going to move us... Oh, thank you, Emily. I am going to move us to the calculus of it all, because even if we're not too comfortable with a function, that doesn't mean we won't understand the calculus of it. And for the calculus, we're going to depend on a couple things. So this is our last step before we get to the calculus of it all. But if we know that we have the arc sine of x, if y equals the arc sine of x, and we're asked to find the cosine of y, this problem here, which is just a trig problem, is actually going to lead us right into the calculus that shows us how we got those derivatives at the beginning of class, when I had you look at the front flap problems, or derivatives 19 through 24 on the front flap. So when you're looking at a problem like this, it's all going to be about draw it out. So I know from what I'm given that if I were to draw a triangle, when I'm using the inverse functions, the thing that the arc sine equals is my angle. So that means here that my angle is right there. If I rewrite my function, I've got this. And remember, trig functions use ratios. So realistically, I do need to write it with something where I can see the opposite over the hypotenuse. And I can go ahead and put in my opposite and my hypotenuse side. And then I lean back on our old favorite Greek mathematician, Pythagoras. And I say, okay, I can see that I've got an A, a B, and a C side. And I know that A squared plus B squared is equal to C squared. And I can use it to solve for my missing side. And now I can say that I can find the cosine of y because it's going to be the adjacent side divided by the hypotenuse. And yes, we're not getting out anything with numbers here, we're getting out equations. But equations are actually going to be what's going to be helpful for us when taking the derivative. So we were given a relationship between y and x. We use them to put them on the triangle. And then we use our past knowledge to complete the triangle in a way that allows us to find the other trig function it asks for. That uses different side lengths to find its ratio. What we're doing today is some pretty sophisticated math. Gabe says, yep. All right, and through all that, we haven't even gotten to the calculus yet. That's all been pre-calculus. But again, that's just because it's pre-calculus doesn't mean that you've seen it, doesn't mean you've spent enough time with it. Like, don't feel like I'm saying that, because goodness knows that's not what happened for most people last year. Alright, I'm going to go ahead and scroll, but if you need me to not scroll, stop me. Because now let's get to the calculus. So I showed these to you at the beginning of class, what your derivatives equal, but let's prove it to you using the knowledge from that last problem we just did. So we have a function, we're going to go ahead and call it y, and it's going to equal the arcsine of x. So what we're going to need to do is if it's helpful to you, go ahead and convert this to a sine. This means that the sine of y would be equal to our x, which would be equal to our x over 1, of course, because we do need to see it in ratio format. And then do, most definitely, make a triangle out of that situation. And use Pythagorean's theorem, which we just did, I know, but I'm going to do it again. Use that to find your missing side. And I will pause for a moment here to let you catch up. But what we're going to take the derivative of is the thing we already know how to take the derivative of. And while I've given you the derivative of the arcsine, it's not, we don't know how to do it yet. It just would be memorizing, and memorizing is not the same thing as knowing how to do it, where it came from. So we do know how to take derivatives of sine, though. We've done that for months now. What is the derivative of a sine?
Sine.
What was it?
Cosine.
Cosine. Okay. I heard just sine, and I think just your microphone hadn't unmuted yet. And I was like, well, it's on itself. But it is cosine. And remember, it's been a little while since we played with this, but when your variables don't agree, we have to use implicit differentiation. And so you have to take the derivative of y with respect to x. We have some implicit differentiation on the left. On the right, what is the derivative of x? This one you can even show me with your fingers. JC's showing me. Andrew's showing me. Keaton's showing me. If Gabe is showing me, it's off screen. Aurora showed me super fast. Sathya showed me. We get 1 out of that. All right, now I can rearrange to solve for my dy dx. And that's the trick right here. We started with y equals the arcsine. So when we find the dy dx, we have found the derivative of the arcsine. The only thing is our derivative has a y value in it, and we don't like that. We want to deal with that. But we have found this is the derivative of our arcsine. The derivative of the arcsine of x could be defined as 1 over the cosine of y. And then this triangle that we made at the beginning, but then ignored for a moment, this is where we are going to come back to that and say, okay, a cosine of a y value is going to be its adjacent side over its hypotenuse. And then we use our rules about what happens when we have a fraction divided by a fraction. To find this insane claim that we had made at the beginning, that when we took the derivative of a inverse trig function, we get out an algebraic rational function. All right, are your minds blown? Are they hurting? Well, we're not done yet. Normally I would say, okay, well, I've hurt you enough, but we're not done yet. I've got still plenty more prepared for today's lesson. But we'll pause and let you guys finish copying this down. I'm not going to do proofs of all of the trig functions, but I do have 2 more proofs prepared for you. I do have proofs on the basic 3 trig functions, so sine, cosine, and tangent, or rather the inverses of each of those. And for time's sake, if we don't finish the lesson today, I'm just going to make a video and finish it that way. I'm not going to take another day on this, just because we do really need to not... There are certain things we can't spend 2 days on just to be able to get through all the material for the AP test. And that's where, if you need some extra time, I'll make all the videos you want or need on this subject. I can't necessarily pause and sit on this subject for very long. Okay, I'm going to give you about 30 more seconds to finish copying. And then if you don't get it, you can... I'll absolutely make sure I get this video up tonight. If you do need to go back and recopy any of these things. Or you can always take a screenshot and then come back and finish copying. Aurora, I'm sorry about the tension.
I don't believe that you can through the BYU Wi-Fi, and I'm
So I actually, last night I started to get a little sick, and I was like, oh, whoa, what's going on? Because the only time I felt this way was after my COVID vaccine. I can't imagine how I would have gotten COVID because I've stayed home so much, but I know I had a headache last night. I don't know if if it's a tension headache you've got, but I know I got a little something last night. You might be able to hear it because I can hear it in my voice, my cold or whatever I've got going on right now. Alright, so we're going to take the derivative of our arc cosine here, but even though I did tell you at the beginning of the lesson what this derivative equals, I'm not going to tell you again. We're just going to go through this as a proof to discover what it equals. So we're going to use that trick again, that we're going to say that y is equal to our function, and therefore the cosine of our y is the ratio. And I use that to make a triangle. This time my x is in the adjacent location, but the hypotenuse is still the same. And then I'm going to use Pythagorean's theorem to find that missing side, and very conveniently, I'm going to end up getting the same thing I got before. When we do tangent, of course, we will not. We will get something different based on this process.
Okay, so the reason I'm asking.
Give me a second.
So the OIT or the Office of Information Technology for BYU, they have
Okay. Yeah, you guys probably know by now, my husband and I have our offices set up next to each other. And he's on a phone call right now. You probably could hear it all. You might still be able to hear some of it. Alright, so now we're going to get into the derivative of it all. And what we're going to do is we're going to take the derivative with respect to x of the cosine function that we already know. But that cosine function does have to be cosine of y is equal to x for it to yield the inverse's answer. And the derivative of a cosine is a negative sign. Your variables do not agree. You have a y and you're taking derivative with respect to x, so you do have to multiply by the derivative of y with respect to x. And then we're going to take the derivative of the other side, and we get out just 1. And then I use my triangle to finish this off. I need the opposite side, and I need the hypotenuse. And remember, this works because dy dx references this equation right here. So when we take dy dx, we are taking the derivative with respect to x of the arc cosine. I thought about telling you at the beginning of the lesson about how these are some of my favorite derivatives, like I often will, but I knew by now, you guys know, if she says that, there's something going on with these, and I thought I would save that surprise until we got into the lesson. Oh, we lost somebody. Okay, go ahead and take a screenshot if you haven't got this copied yet. I'll give you a moment for that. This is pretty, I knew today was going to be a pretty intensive day on notes. Okay. All right, and like I said, I'm not going to do all the trig functions, but I am going to do one more. We're going to prove, the derivative of the arctangent as well. And for the other 3 trig functions, the proofs would be similar, but I'm not going to do those. So first thing we're going to do is we're going to establish that our y is equal to this, which means we can rearrange the function And these two, if we were to graph these, by the way, they are the exact same function. When I haven't switched my x and my y's yet, if I were to graph these are the exact same graph. Now I'm going to be looking at it in terms of opposite over adjacent. So that changes what I see where. I'm going to have this here and this here. Nothing on the hypotenuse yet. And I use the relationship to make the triangle because while I don't need it yet, one of the most important things you're going to need in this process is the triangle to do that last step. Cormac, your camera froze mid-yawn, and it's amazing. And I saw you unmuted yourself, but I didn't hear what you said. I don't know if your mic's working or not. All right, so so we're going to take the derivative with respect to x of the tangent of y and what the tangent of y equals. And do you remember what the derivative of a tangent is? It starts with an S. But it's not sine. And there's a squared involved. And I've just given you the whole thing.
Sec squared.
Secant squared of y. And believe you me, that is one most absolutely memorized. The AP test will love derivatives of tangents. That will show up multiple times. And your derivatives, our variables do not agree, so we do have to multiply in by that derivative of y with respect to x. On the other side, we have a much easier derivative, just equal to 1. Divide both sides by secant of y, and we get 1 over secant squared of y, which on this case, I didn't do it before when I was dividing by cosine, but on this case, I am going to go ahead and say, you know what? 1 over secant is the same thing as a cosine, so this is the same thing as cosine of y squared. And then once I have established what my derivative is in terms of y, I go back to my triangle and I use it to find the cosine of y. So my cosine is the adjacent side over the hypotenuse and then I'm going to square it very conveniently. The square and the square root cancel, and of course 1 squared is just 1, so I end up with 1 over 1 plus x squared as my derivative. Now, for me personally, I've brought this up before, I don't memorize well. So for me, remembering this process is easier than trying to memorize which ones are which, what the derivatives are equal to. For you, memorizing might be easier. And honestly, too, I remember the first time I learned these, I just felt like they were out of left field, and even the process took me a while to get used to. I don't think I got used to it, in fact, the first year it was taught to me. But use whatever method works best for you. I would expect the AP test to include derivatives of especially arcsine, cosine, and arctangent. The other three functions, maybe you'll see one question on, but these ones right here, I would expect that you would see up to 3 questions, I would say, on the AP exam using those 3 derivatives, or an integral that involves them, which we'll get into the integrals later. All right, but what I want to finish off with is I want to get through at least one chain rule question. And for this, if you just have your front flap open, that is going to be good enough for me. So, let's find the derivative of the arcsine of 2x. And what's going to happen is the thing that's in the x location is, if you look in your book, they have a u there instead. You might have seen that from the beginning. I was using x's, but they had u's. You can go through the whole process and prove this. Most absolutely, you can do that. And in fact, for me personally, that is what I would be more inclined to do. Let's see, so it's 2x squared plus b squared equals 1 squared. And I know I'm going kind of fast, but it's because I see the time. So for me personally, that method is easier than to have the memorization. Where the memorization would be, you just say, oh, the thing that's in the x location changes to 2x, and then you have to take the derivative of the inside. This method, while it might look a lot shorter, and for some of you, this will be the preferred method because you memorize better than I do. This is all about taking the derivative of the outside times the derivative of the inside and using the chain rule. But to do that, you will have to memorize this function here. And if you're somebody who memorizes well, it'd be worth it. If you're like me and it's not something you memorize well with, the process of working it out and problem solving is going to actually be the easier one. And it's just going to depend on personal preference. Okay, so class is ending right now, but don't leave yet because I am going to take roll because I know some of you had come in tardy and I want to make sure I give you credit for being here. But I will plan on making another video for you where I'll do some more examples. And we're not going to do a second day on this lesson. So make sure, I'll do it as a second video. Make sure you catch that second video to get ready for what we're doing here.